So our today's topic is solubility of solids and gases in liquids. So let's study our first topic, solubility of solids in liquids. So first of all, what is solubility? The maximum amount of solute that can be dissolved in 100 gram of solvent at a given temperature is termed as its solubility at that temperature. Depending upon the amount of solute dissolved, solution can be of two types. First is saturated solution, a solution which contains maximum amount of solute dissolved in a given solvent at a particular temperature. So saturated solution is that solution in which no more solute can be dissolved in a given solvent. And second is unsaturated solution, a solution which contains less amount of solute than required for forming saturated solution. Depending upon the solubility of two components in one another, solution can be of three types. First is miscible solution. When the two components completely mixed with each other, in this case the two liquids are of the same nature, that is they are either both polar, for example ethyl alcohol and water, or both non-polar in nature, for example benzene and hexane. Second solution is immiscible solutions. When two components are not mixed with each other or there is no mixing, here one of the liquid is polar and the other is non-polar. So that means the nature of both the liquid is not same. For example, edible oil and water. And third type of solution is partially miscible solution. When the two components are partially mixed or when there is a partial mixing, that means it form partially miscible solution. For example, ether and water exhibit partial miscibility. So let's study what are the factors which affect the solubility of a solid in a liquid. So first is the nature of solute and solvent. So if I'm asking from you that to whom would you like to talk or share your feelings, then it is a person whose nature is similar with yours. So just like that, why substances dissolved in one another? The answer is like dissolves like. Whether or not two substances form a solution depend upon their nature. That is, polar solids dissolve in polar solvents. On the other hand, non-polar solids dissolve in non-polar solvents. For example, ethyl alcohol or ethanol dissolves in water. Although ethanol is a covalent compound, but it is polar in nature and is dissolved in polar solvents like water. When mixed together, ethanol and water molecules attract each other because of the formation of hydrogen bonds. On the other hand, benzene and toluene are soluble in each other because both are non-polar aromatic hydrocarbons and have similar molecular structure. These non-polar covalent solids dissolve in non-polar solvents because of the van der Waals interactions between solute and solvent molecules. Second factor is the effect of temperature. Most ionic and molecular solids become more soluble at higher temperature. This depends upon the enthalpy of solution. So it can be divided into three categories. So first is, if the solute dissolves with absorption of heat, that means the reaction is endothermic. So in that case, the solubility increases with the rise in temperature. For example, sodium nitrate, silver nitrate, sodium chloride, potassium chloride, etc. As shown in the graph, the curve is almost straight line for these solutes. So that means the solubility increases with the increase in temperature. So in second case, if the solute dissolves with the evolution of heat, that means the reaction is exothermic. The solubility decreases with the rise in temperature. For example, in lithium sulfate, This is in accordance with Le principle. However, in some solids like sodium sulfate, the behavior is not regular, as shown in the graph. In the beginning, the solubility increases with the increase in temperature up to certain limit. Then it decreases. The temperature at which the solubility is maximum is the transition temperature. In this case, it is 32.8 degrees Celsius. This is due to the change in one solid form to another solid form. That is, sodium sulfate hydrated changes to anhydrous sodium sulfate. So this is all about the effect of temperature on the solubility of solids in liquids. So let me tell you one thing, that the effect of pressure on the solubility of solids in liquids is negligible, as solids and liquids are incompressible. Our second topic is the solubility of gases in liquids. So it may be expressed as the volume of gas in cubic centimeter that can be dissolved in a fixed volume of the liquid to form the saturated solution at a given temperature.
Papa, as we know, all living beings can't live without oxygen. We take oxygen from air. Then from where fishes take oxygen?
For breathing, fishes take dissolved oxygen from the water.
How we will come to know that gases are present in water?
Let me show you by doing a simple activity. Take a sealed bottle of any soft drink. Are you able to see any gas in it?
No.
Now try to open the bottle. What's your observation?
Bubbles are coming out with a fish sound.
I will tell you now that what had happened. Actually, carbon dioxide gas is dissolved in the drink under high pressure. When you open the bottle, the pressure falls, and the soluble carbon dioxide gas comes out from the drink with a fizz sound in the form of bubbles. Let's now discuss the factors affecting the solubility of a gas in a liquid. So first is the nature of gas and the solvent. Gases like nitrogen, hydrogen, oxygen, helium, etc. dissolve in water only in a small extent, whereas the gases like ammonia, sulfur dioxide, hydrogen chloride are highly soluble in water. The solubility of these gases in water is due to the chemical reactions of these gases with water to form ammonium hydroxide with ammonia, sulfuric acid with sulfur dioxide, and hydrochloric acid from the hydrogen chloride gas, respectively. Next, second is the effect of temperature. The solubility of a gas decreases with the increase of temperature. This is because in general gases dissolve in liquid with the evolution of heat, that is exothermic reaction. So therefore, in accordance with Le principle, the increase in temperature will result in decrease in solubility of gases. So our third factor is the effect of pressure and Henry's law. The solubility of gases increases with the increase in pressure. This is also in accordance with Le principle. So let's discuss this effect by taking two cases. First is when the pressure is low. Since there is a dynamic equilibrium with the number of gas molecules entering the solution is equal to the number of dissolved molecules leaving the solution phase. So in case when pressure is low, less number of molecules are in the gaseous state, and that's why the molecules which strike the liquid surface are also in less count. On the other hand, when pressure is high, the increase in pressure increase the number of gaseous particles per unit volume over the solution. As a result, more molecules will be striking the liquid surface, and hence more molecules will dissolve, and thus the solubility of gas increases when pressure is high. Henry's law. Gases dissolve in liquids to form homogeneous solutions. William Henry gave a quantitative relationship between the solubility of gas and pressure. Definition of Henry's law is the mass of a gas dissolved per unit volume of the solvent at a given temperature is directly proportional to the pressure of the gas in equilibrium with the solution. That is, small m is directly proportional to P, or m is equal to Kp, where m is the mass of gas dissolved, P is the pressure of gas, and K is the proportionality constant. So when the solubility of gas is plotted against the equilibrium pressure for different gases, a straight line passing through the origin is obtained. Alternatively, if we use mole fraction of gas in place of mass of gas, then the pressure of gas over a solution in which the gas dissolved is proportional to the mole fraction of the gas in the solution. That is, small x is directly proportional to P, or x is equal to K dash P. Or we can say that P is equal to 1 upon K dash into x. From here, P is equal to KH into x, where KH is 1 upon K dash, and KH is the Henry's law constant, and its units will be atmosphere bar, as same as that of pressure. So let's discuss some points related to Henry's law constant. First is, the higher the value of KH at a particular temperature, the lower is the solubility of the gas. So from the formula, it is clear that KH is inversely proportional to mole fraction of gas dissolved. So that is why if the value of KH is high, the solubility is less. The second is, the value of KH increases with the increase in temperature. Thus, higher the temperature, lower is the solubility. That is why aquatic species are more comfortable in cold water than warm water. And third is, Henry's law constant KH depends upon the nature of the gas. So let's discuss the applications of Henry's law. So first is, to increase the solubility of carbon dioxide in soft drinks, the bottles are sealed under high pressure. When the bottle is opened, the pressure inside the bottle falls and the excess carbon dioxide bubbles out of the solution with a fizz sound. Second application is in lungs. In human bodies, in lungs, the partial pressure of oxygen is very high. Thus, it combines with hemoglobin, which is present in our blood, to form oxyhemoglobin. In the tissues, the partial pressure of oxygen is low, and thus the oxyhemoglobin releases oxygen to the tissues for cellular activities. So third application is, at high altitudes, the partial pressure of oxygen is less than that the ground level. This is because at high altitudes, the air is less dense. This results in low concentration of oxygen in the blood of people living in high altitudes, which causes weakness or anoxia. So moving to next application, to minimize the painful effects of deep sea divers, oxygen diluted with less soluble helium gas is used as breathing gas because of the low solubility of helium in blood. Moreover, because of small size of helium atoms, they can pass through cell wall without damaging them. So, last is the limitation of Henry's law. Henry's law is valid only when the pressure is low, second, the temperature is not too low, the gas is not highly soluble, and the last is the gas neither reacts chemically with the solvent nor dissociates or associates in the solvent. Let's try one numerical based on Henry's law. 1 liter of water under nitrogen pressure of 1 atmosphere dissolves 0.02 gram of nitrogen at 293 Kelvin. Calculate Henry's law constant. So in this, weight of nitrogen is given, which is 0.002 gram. Volume of water is also given, which is 1 liter, or we can say 1000 milliliter. Pressure is also given, which is 1 atmosphere. We have to find out the Henry's law constant, that is Kh. So according to Henry's law, P pressure is equal to Kh into X, where X is the mole fraction of nitrogen. So first of all, we have to find out the mole fraction of nitrogen. So number of moles of nitrogen, that is equal to weight of nitrogen divided by molecular weight, which comes out to be 7.143 into 10 raised to power minus 4. And number of moles of water, which is the weight of water divided by molecular weight, that comes out to be 55.5. Here the density of water is assumed to be 1. So from the number of moles of both the components, let's find out the mole fraction of nitrogen, which is the ratio of number of moles of nitrogen divided by total number of moles of both the components, which is equal to 7.143 into 10 raised to the minus 4 divided by 7.143 into 10 raised to the minus 4 plus 55.5, which comes out to be 1.29 into 10 raised to the minus 5. So Kh is equal to pressure upon mole fraction of nitrogen, which is equal to 1 atmosphere pressure divided by 1.29 into 10 raised to the minus 5, that is a mole fraction of nitrogen. That comes out to be 7.75 into 10 raised to the 4 atmosphere. Students and my friends, please subscribe my channel and click the bell icon for further updates. If you have any query or suggestion, please write down in the comment section. Thanks for watching.